Problem 1, find the relative extrema of f of xy equals negative 2/3 x cubed plus 4xy minus 2y squared plus 1. Okay, so we know we just need to find the gradient of f and then set each component equal to 0. Gradient f is going to be negative 2x squared plus 4y, comma, 4x minus 4y squared, 4y. Okay. Setting these equal to each other, or just seeing, we're going to have x equals 0, y equals, sorry, that will not work. We need to actually negative 2x squared plus 4y equals 0, and 4x minus 4y equals 0. We're going to have 4x equals 4y, therefore x equals y. We can plug in x right here pretty easily. Negative 2x squared plus 4x equals 0. Factor out of negative 2x, x minus 2 equals 0. X will be 0 and 2. Therefore, y equals 0 and 2 as well. And looks like A, B, and C can't be it because 2 is our only candidate point. And we don't even really need to check if the determinant is greater than 1 or greater than 0, to be exact, just because it already told us it's either a max or a min. So computing the second partial derivative, let's just take this one. That would be the easiest. It's just negative 4. And if we think about it, when it's negative, the slope is kind of decreasing, so we're very positive here, 0 here, and then we're negative, so it will be a local maximum. Consider the surface z equals 3 minus x squared minus y squared plus 4y. Find all points on the surface at which tangent plane is horizontal. Okay, so this is pretty much the same problem. Tangent plane horizontal is just going to be where we have a local min or max. If you think about it, if we have a paraboloid, tangent plane is only going to be horizontal, where we have kind of the gradient is going to be equal to 0, which implies it is a local min or max. So finding z, or I should just say gradient of fxy is just equal to z. It's just going to be negative 2x, negative 2y plus 4. Setting these equal to each other, we're going to get negative 2x equals 0. Therefore, x equals 0. Negative 2y plus 4 equals 0. Y equals 2, so we have 0. 2, that is our only critical point, so B has to be our answer. 3, find the maximum value of f of xyz equals x squared, or x plus y plus z, subject to this constraint. All right, so this is again going to be min-max problem, but Lagrange multipliers this time. And we know grad f equals lambda times grad g in Lagrange multipliers. Grad f is going to be equal to 1, 1, 1. Grad g is going to be 2x minus 2, 2y, 2z. And we just have to set them equal to each other. So 1 equals lambda times 2x minus 2. 1 equals lambda times 2y. 1 equals lambda 2z. And setting that and that equal to each other, we're just going to get y equals z, which is going to make it much easier for us. And okay, so solving for x is going to be pretty useful too, just because we can plug it into our constraint function and actually solve for lambda. So we're going to get 1 equals 2 lambda x minus 2 lambda. Therefore, 1 plus 2 lambda equals 2x, 2 lambda x, and x equals 1 plus 1 over 2 lambda. And we can do the same thing for y or z. It doesn't really matter since we know y equals z. So z is going to be equal to 1 over 2 lambda. And that's weird because that's kind of the same thing here. So we're going to see some overlap, and that's going to be very nice. So plugging in x into our constraint function, we are going to get 1 over 2 lambda squared plus 2, because we know x equals y. 1 over 2 lambda squared, and that is equal to 1. And we can just see that adding these together, we can get 3 times 1 over 4 lambda squared equals 1 over, not 1 over 3, just equals 1. And taking the square root of both sides, we are going to get plus or minus 1 equals root 3 over 2 lambda. So setting our lambda equal to positive 1, so we're going to get 1 equals root 3 over 2 lambda. Therefore, lambda equals root 3 over 2. And also, we're just going to write that lambda also equals negative root 3 over 2. And now we see that we're looking for the max of f. And since we have lambda as that, we know that we can find our z value pretty easily, and therefore our y value. So plugging in that, we know that we're going to use the positive value of lambda because we're looking for the max. We're not looking for the min. So I guess if I move this over here, it'll make it a little bit easier. Plugging in lambda equals root 3 over 2 here should be pretty simple. We're going to get z equals 1 over root 3 equals root 3 over 3. And we know that that's the same thing as this, and we're going to have 3 of those because y equals x. So we're going to have root 3 plus 1 as our answer here. And how I did that was add that to 2 times that because z equals y, and then plug it into our x, and we are going to get root 3 plus 1. So A is our answer. Number 4, the x-coordinate of the plane, or the point on the plane z equals x plus y, that is closest to the point 1, 1, 1 is equal to. So you can do these problems multiple ways. I prefer kind of the way of thinking about it like the normal vector to the plane. So if we have z equals x plus y minus z, we know that the normal vector to the plane is just going to be equal to 1, 1, negative 1. And we know if we have a plane, the closest point is going to be, or to the plane, is going to be on that normal vector. Because if you're going at a diagonal, you're always going to be taking a longer path. The normal is always going to be the shortest path. So that's going to be kind of our direction vector of the point. So if we plug that in, if we kind of make an r of t, or the line for our point that contains the plane, we are going to have 1 plus t, 1 plus t, 1 minus t, and that has to satisfy our plane equation because we're looking for the point on the plane. So we're just going to plug these values into the plane. We're going to get 1 minus t equals 2 plus 2t. Negative 1 equals 3t. T equals negative 1/3. And we're looking for the x-coordinate. So we just plug it into this. 2/3 done. Nice. Pretty quick. All right, find the average value of the function f of xy equals x squared y over the region R, where R is the rectangle with vertices negative 1, 0, negative 1, 5, 1, 5, and 1, 0. So I always like drawing these out. It really helps me visualize it. So we know the average value is just going to be 1 over the area times the double integral of f xy of the region R dA. And it's going to be pretty easy to compute A because it's a rectangle. We just do base times width, or base times height, doesn't really matter. And that is 2 times 5 equals 10. So A is just 10. And looking at that, we're just need to compute the double integral, x squared y, dx dy. X goes from negative 1 to 1, y is 0 to 5. So x cubed over 3, y evaluated at 1, negative 1. That should be y over 3 plus y over 3 equals 2y over 3. and we need to integrate that. Y squared over 3. Or sorry, yeah, y squared over 3 from 5 to 0 would just be 25 over 3. So that is our integral, and that is not our answer because, remember, we need to divide by 10. So 25 over 3 divided by 10 is just 25 over 30, which is 5/6. We almost got tricked by that, but that did not happen. I'm a professional. Number 6, evaluate that integral where r is the region of the xy plane bounded by the x-axis, the line y equals x, and the line x equals 1. So we're looking at the x-axis, and x equals 1. So it looks like that will be our region. And it looks like we shouldn't do dx dy here because integrating that with respect to x is not exactly very possible. So if we just do dy dx, we should solve all of our problems in life and math, whatever. Dx, dy, dx. So we're going from 0 to x because y equals x, and x is going from 0 to 1. That should be, oh, that's pretty nice because we're just going to have sine x dx, integral of that, 0 to 1, because I just integrated that, integrated y, so it becomes y sine x over x, evaluated at y equals x at y equals 0. And the x's cancel here, so we just get sine x. Integral of sine x is negative cos x, evaluated at 1 to 0. Negative cos 1, so we're going to have, okay, I see how it is. I'm going to have negative cos 1 plus cos 0, which is 1. So we're going 1 minus cos 1. Just checking if that's exactly accurate. So if we factor out the negative 1, cos x evaluated at 1, 0, we're going to get cos 1 minus cos 0. Cos 0, so negative cos 1 minus 1. Yeah, that should be our answer. Number 7, rewrite the integral as an integrated integral in polar. Do not evaluate. Nice. I did not want to evaluate this anyways. So we know that's going to be our dA, and in polar, dA equals r dr d theta. X squared plus y squared just equals r squared. And we're taking the square root of that, so we're going to have the integral is going to be r from here times our r. So we're going to have r squared. So a is not our answer, b is not our answer, e is not our answer. That makes it very easy. Dr d theta. And just drawing out our region, it looks like y is going to be the positive. So we're going not from 0 to 2 pi, but from 0 to pi. So C should be our answer, 0 pi, 0, 1, because as we can see, we're going here, and we're going like that. And that is 0 to pi. C. Number 8, reverse the order of integration of the following integrated integral and evaluate. Okay, yeah, I see why they say reverse. You cannot integrate e to the x squared. So let's just draw out our domain, sketch it out. We have x equals 1/2 y, therefore 2x equals y. So we're going to have some line like this. And then x is going to be some constant here. And that point right here is going to be ln, or square root of ln 3. It doesn't really matter that much, but just for correctness. And 2 ln square root 3. Nice. All right, so rewriting it, we are going to get e to the x squared dy dx, and y is going from 0 to 2x, x 0 root ln 3. And as we evaluate this, we're going to get 2x e to the x squared. And that is nice because we can actually integrate that from 0 square root ln 3 dx. And that is just going to be e to the x squared, evaluated at root ln 3 to 0. And that will be e to the ln 3 minus 1, and that is 3 minus 1, that is 2. And just worth noting, you might have forgotten, e to the ln x is just equal to x. That is worth noting. Number 9, convert the integrated integral to cylindrical coordinates and evaluate. All right, so we have a 1 over r situation here. Always good to sketch out the domain. Love doing that. And write out the integral here. We're going to have dz. And we have 1 over root r squared is just 1 over r. So we're going to have an ln here. Or it cancels out because we multiply by r, because it's r dz dr d theta. That is nice. All right. So let's just check the domain here to see our bounds of, actually our bounds for 0 to 0 to r, because plug in r squared for x squared plus y squared over there, and we get that. So y looks like we're going from 0 to that, and x is from 0 to that. So we're looking for this kind of domain here. So that is theta, 0 to pi over 2. R is 0 to 10. And that's very nice because we can take out the theta because nothing depends on theta. Integral 0 to 10 of r dr. So that is just r squared over 2, 10, 0, 100 over 2. That's 50 times pi over 2 because we took it out here. Whoa, did not mean to do that. Equals 25. Whoa, again, going a little too fast here. 25 pi. That is D. Number 10, let V be the volume of the solid bounded by the surfaces. Z equals 6 minus x squared minus y squared. And Z equals x squared plus y squared. So these are two, if you draw them out, these are just going to be two kind of paraboloids. Very nice. I love paraboloids. And then positive one right here. So I'm guessing, oh, we're using regular coordinates. Interesting. All right, so just looking at this, I'm very proud of myself for this drawing. I really like it, actually. Should go on some award. Anyways, we're looking for B and A. So we're looking, Z is going from, it's looking like the positive paraboloid to the negative one. So B just should be 6 minus x squared minus y squared. So C just looks like an answer. Looks pretty easy, to be honest. Looks a little too easy. And let's check by setting our bounds equal to each other. So 6 minus x squared minus y squared equals x squared plus y squared. So I set these, the B equal to the top bound, equal to the bottom bound. And just checking, yup, it does look pretty accurate. And anyways, it has to be, B has to be that, because we will be hitting, we will be hitting the negative paraboloid. Number 11, which of the following integrals represents the volume of the solid inside a sphere of radius 2 and outside, radius 2 centered at 0, 0, 2, and outside a sphere of radius 2 centered at 0, 0, 0. Yeah, this is quite a difficult problem, I'd say. I probably wouldn't have known this the first time I took Calc 3. Not saying I failed or anything, but just drawing the radius out here, we are going to get like some sphere like that and also some sphere like that. And we're looking for this domain kind of right here. And if we draw the cross section, I think that'll help. So if we draw the YZ cross section, it's just going to be a two-dimensional coordinate plane. And that's going to be our first circle. That is going to be our second circle. And if you can see, the rho value should be going from 2 to 4, where the 4 is the maximum. But this 4 is also going to change depending on where we're going, because this is not a constant rho value. That is going to depend on the phi value, just because if you think about it, it's not going to be, the sphere is shifted up. It's not centered at 0, 0, 0. So C is not going to be our answer, and E is not going to be our answer. And B is not going to be answer because we should be starting at, and D is not going to be our answer. So A should be our answer. And why that makes sense is if we write out the equations for our spheres, we're going to have x squared plus y squared plus z squared for the one centered at 0, 0, 0 equals 4. And x minus 2 squared plus y squared plus z squared equals 4. And expanding those, if we just set them equal to each other by the 4s, we can just cancel these. So we're going to get x squared minus 4x plus 4 equals x squared. Cancel out these. We are going to get 4x equals 4. That means x equals 1. And if we think about it, x is just going to be, that's going to be our x value that intersects. And it makes sense that it's going to be 4 cosine phi here, just because when phi is 0, cos phi is at a max. And that's kind of what we want at the top. That's going to be our max phi value. So 11 is going to be A. Number 12, find the x-coordinate of the center of mass of a plate in the shape of the region bounded by y equals x, y equals 1/2 x, and x equals 1, with a density sigma of xy equals 2x. And recall that the mass moments about the x and y axes are mx equals y times sigma xy dA, and my equals x times sigma dA, respectively. So we want the x-coordinate. So that just means we want basically my over the total mass. And I think it makes sense to find the total mass first. And that's just going to be the double integral over the region that they gave us of the density. So starting at the integral, it's going to be 2x, obviously. I'm going to do dy dx. That'll make it easier. So we're going 1/2 x to y equals x. And x is going from 0 to 1. Very nice. So taking out the 2 to make it easier, so the outer integral, keeping that, we're going to get x times just 1/2 x, because since nothing depends on y, quick shortcut is just do top minus bottom. And x minus 1/2 x is just 1/2 x. So x times 1/2 x, and we can see those x's cancel, 2's cancel, not the x's, dx, and that is just going to be x squared over, or x cubed over 3, evaluated at 1 to 0, and that is just 1/3. So 1/3 is our total m. So that just means we're going to multiply the my by 3. So I guess I can just write that out right now. And my is x times sigma. So again, we're going to have the 2 here because we're still integrating the same sigma. And same bounds, so integral, that is a nice integral sign. So 1/2 x, x, 0, 1, but this time it's going to be x squared dy dx. And just looking at this, again, we can do top minus bottom here because nothing depends on y. Very nice. We're going to get x squared times 1/2 x, and integral that, 6 times dx, again 0 to 1. I'm going to take out a 2 here, just make that a 3. So that'll be 3 times 0 to 1, or I don't even need to write that. We know it's just x cubed. So 3 times x cubed over 3. My bad. It is x to the 4th over 4, because this is, inner is just x cubed from 1 to 0, and that is just 3/4 is our answer. So our answer is D here.